In section 4.2, we discuss prefix codes, which is a very important class of uniquely decodable codes. Definition 4.9. A code is called a prefix code if no code word is a prefix of another code word. For brevity, a prefix-free code will be referred to as a prefix code. Here is an example of a prefix code. Consider the code C', which maps A to 0, B to 10, C to 110, and D to 1111. It is easy to check that no code word is a prefix of another code word, and therefore C' is a prefix code. A DRE tree is a graphical representation of a collection of finite sequences of DRE symbols. For such a tree, a node is either an internal node or a leaf. The tree representation of a prefix code is called a code tree. Now let us discuss instantaneous decoding of a prefix code. Using the code C' in example 4.10, B is mapped to 10, C to 110, D to 1111, A to 0, and C to 110. Upon concatenating the code words, their boundaries are no longer explicit. That is, from the stream of symbols, we cannot tell the ends of the code words. The stream of coded symbols are then transmitted to the receiver. Since C' is a prefix code, the code words can be represented by a code tree, which is shown here. In labeling the nodes of the tree, we adopt the convention that going up is 0 and going down is 1. So we have the code word 0 for A, the code word 10 for B, the code word 110 for C, and the code word 1111 for D. Now we are going to show that instantaneous decoding at the receiver can be done by tracing the code tree from the root. Now consider the stream of symbols received at the receiver. First, we receive the symbol 1. So starting from the root, we trace down, and then we receive the symbol 0. So we go up, and then we reach the code word 10. And then we put a comma, denoting that this is the end of the code word. Now the next symbol received is 1, so we go down. The next symbol is 1, so we go down. The next symbol is 0, so we go up. And then we reach another code word, 110, and we put a comma there. Now the next received symbol is 1, so we go down, 1, go down, 1, go down, and 1, go down. Here we reach another code word 1111, and we put a comma. The next received symbol is 0, so we go up and reach a code word 0, and put a comma. Now the next symbol is 1, so we go down, 1, go down, 0, go up. So we reach the code word 110, and we put a comma, so on and so forth. The boundaries of the code words can thus be recovered. In this sense, a prefix code is said to be self-punctuating. Theorem 4.11 is a characterization of the existence of a DRE prefix code. It says that there exists a DRE prefix code with covert lengths L1, L2 up to Lm if and only if the Kraft inequality summation d to the power minus Lk, k equals 1 to m, less than or equal to 1, is satisfied. The direct part of the theorem, that is, the only if part, follows because the prefix code is uniquely decodable and hence satisfies Kraft inequality. We now prove the converse, that is, the if part of the theorem. We need to prove the existence of a DRE prefix code with covert lengths L1, L2 up to Lm if these lengths satisfy the Kraft inequality. Without loss of generality, assume that the covert lengths are indexed in ascending order. Consider all the DRE sequences of lengths less than or equal to Lm and regard them as the nodes of the full DRE tree of depth Lm. This is illustrated in the figure. We will refer to a sequence of length L as a node of order L. Now there are d to the power L1 greater than 1 nodes of order L1 which can be chosen as the first covert, because we assume that L1 is greater than or equal to 1. This is illustrated in the figure. Thus, choosing the first covert is always possible. Assume that the first I coverts have been chosen successfully, where I is between 1 and m minus 1. And we want to choose a node of order L I plus 1 as the I plus first covert, such that it is not prefixed by any of the previously chosen coverts. Since all the previously chosen coverts are not prefixes of each other, their descendants of order Li plus 1 do not overlap. The I plus first node to be chosen cannot be a descendant of any of the previously chosen coverts. This is illustrated in the figure. Consider the full tree of length Li plus 1. The number of nodes of order Li plus 1 is equal to d to the power Li plus 1. For a node of order L1, the number of descendants of order Li plus 1 is equal to d to the power Li plus 1 minus L1. Because the depth of this subtree extending from that node is equal to Li minus L1. Likewise, for a node of depth L2, the number of descendants of order Li plus 1 is equal to d to the power Li plus 1 minus L2. And for the node of order Li, the number of descendants of order Li plus 1 is equal to d to the power Li plus 1 minus Li. Therefore, the number of nodes which can be chosen as the I plus first covert is precisely equal to d to the power Li plus 1 minus d to the power Li plus 1 minus L1 minus d to the power Li plus 1 minus L2 minus all the way to d to the power Li plus 1 minus Li. If L1, L2 up to Lm satisfy the Kraft inequality, we have summation k equals 1 up to m d to the power minus Lk is less than or equal to 1. Therefore, the first I plus 1 terms in the summation is also less than or equal to 1. That is d to the power minus L1 plus all the way to d to the power minus Li plus d to the power minus Li plus 1 is less than or equal to 1. Multiplying the above inequality by d to the power Li plus 1, we have d to the power Li plus 1 minus L1 plus all the way to d to the power Li plus 1 minus Li plus d to the power Li plus 1 minus Li plus 1 less than or equal to d to the power Li plus 1. Now, for d to the power Li plus 1 minus Li plus 1, it is just equal to 1. For the remaining terms on the left-hand side, upon moving it to the other side and rearranging the terms, we have d to the power Li plus 1 minus d to the power Li plus 1 minus L1 minus all the way to d to the power Li plus 1 minus Li greater than or equal to 1. Now we recognize that the left-hand side of this inequality is exactly the number of nodes which can be chosen as the I plus first coword. And we have shown that this is greater than or equal to 1. Therefore, we have shown by induction the existence of a prefix code with coword lengths L1, L2 up to Lm, completing the proof. We now introduce a special class of probability distributions. A distribution is called d-adic distribution if pi is equal to d to the power minus ti for all I, where ti is a positive integer. When d is equal to 2, it is called a dyadic distribution. A corollary of the previous theorem is the following. There exists a DRE prefix code which achieves the entropy bound for a distribution pi if and only if pi is d-adic. Here is the proof of the corollary. We first prove the only if part. Consider a DRE prefix code which achieves the entropy bound for a distribution pi. Let Li be the length of the coword assigned to the probability pi. By theorem 4.6, for all I, Li is equal to minus log d pi, or pi is equal to d to the power minus Li. Thus, pi is d-adic. The if part goes as follows. Suppose pi is d-adic. Let pi equals d to the power minus ti for all I, where ti is a positive integer. Then ti is equal to minus log d pi. Let Li equals ti for all I. We now verify that Li, defined as such, satisfies the Kraft inequality. Consider summation I d to the power minus Li equals summation I d to the power minus ti, because Li is equal to ti. Now d to the power minus ti is equal to pi. Now summation I pi is simply equal to 1, and it is less than or equal to 1. Therefore, the Kraft inequality is satisfied. Then there exists a prefix code with coword lengths Li. Assign the code word with length Li to the probability Pi for all I. Since for all I, Li is equal to Ti, and Ti is equal to minus log d Pi, we have Li equals minus log d Pi. We see from theorem 4.6 that this code achieves the entropy bound.